Let's continue our exploration of how BGP works mechanically inside routers by looking at a second example, a variation of the previous one. Now we have three routers in ASX. R1 and R21, R21 and R22 are on link of each other. R1 to R22 are not on link, so the path from R1 to R22 goes via R21. So R21 is acting both as a BGP and OSPF router, if you want, in this case. All three routers in this domain are running both OSPF and BGP. I'm assuming also a small variant. R3 here is advertising only the prefix that's directly attached to it. So it advertises only the 10.1, and this one here, R4, advertises only the 10.2. That's one of the flexibilities that exists in BGP. The topic is how do we originate a route? Those routes are inside the domain. They're not repeated from BGP, so you must bootstrap their existence into BGP. There are multiple ways of doing it. We see here two different ways. The first way in the previous example was all routers inside the domain advertised all the routes in the domain. Here we have something more selective. Some routers advertise some fraction of the routes. Some other routers advertise another fraction. Usually it's the first method that is used, but let's see what happens if we use the second one here in this example. I'm assuming here R3 sends to R1 this message, which is the route 10.1, AS equal Y, and R4 sends this equivalent message with the different destination prefix to R21 and R22. So I continue focusing on, in which order? Whoops. I focus on R1 again, so I am here on R1. When R1 receives this message, there's only one prefix message to this destination, so it keeps it, and it's the best, and it will send it, it will repeat it to its two peers inside X. That's business as usual, as we have seen, right? Now, sooner or later, R22 here, that has received a similar message from ASY, will also send it to R1 over its TCP connection. The dotted lines here means the TCP connection. So both R21 and R22 will do it. Now the system is distributed. The timings are hard to predict. One thing may happen before the other. So I'm assuming here R22 sent it first. So R22 sends this route, this prefix. The AS path should be XY here, sorry. Next hop, 2221, which is this address here, 2221. Now, since it's the only route to this prefix, R1 keeps it and repeats it also to only R1 will repeat it to will not repeat it to R21 or R22 because it was learned internally. It will also not repeat it to R3 because the path contains already the AS path Y, so that would create a loop. So one of the rules of BGP is when you have a path that contains a domain Y, you don't send it to domain Y. A route with such a path is not sent to domain Y. So this is not repeated to anybody. Now, a bit later, the same thing from R21 will come. So R1 will receive the same route, but from R21. It's not exactly the same route. The difference is the next hop. The next hop is now this link here. There is a small mistake here. The AS path inside ASX should be XY and not Y, but let's ignore that for the time being. Which one now will R1 select? R1 has now two routes to the same prefix, 10.2. Which one will it select? Assume you are a BGP router for a few minutes. What would you do? And we have a tie between A and B. The correct answer is yeah, is A. Yes, it will be promoted. Why is that? Well, let's look at the answer is with the decision process. What does the decision process do? It has two routes to compare. It will compare weights and local pref that are not present, so ignore them. It will compare the AS path, which is the same. They both have the same AS path, which is in fact XY. They both come from an IBGP peer, because both R21, where's my R21 and R22 are both IBGP peers. But they don't have the next hop, the same next hop. So another criterion of the decision process is distance to next hop. The next hop will be used by BGP to send the traffic to the next hop. So the semantic of the next hop is not just an abstract field in the table. The semantic of the next hop means if I use this one, if I keep this route 221, which is this leg here, the traffic to this destination will, inside ASX, will be sent towards this address. So the next hop decides what is the exit point we will choose to this destination here. And one of the rules which makes sense is, if you don't know which of the two next hop to choose, because all other criterions are the same, well, choose the one that is closest in the sense of the distance computed, for example, by OSPF. That's called the IGP distance. So here, if I'm assuming OSPF gives same weights to the different, well, in any case, R21 is closer to R1 than R22. So this here is further away than that. So 221 is further away than 331. So R1 will change its mind and will pick this one here. It will choose the thing that is closer, which is this one here. So in summary, in this case, R1 had two ways to go to this destination. One that was via this leg, another one that was via this one, and it picked the closer one, which makes sense here. So this is how BGP will make its decision. Let's see what are the implications of these choices that are made by default by BGP. We'll see a bit later how to change the default by playing with different priority fields. But by default, this is what would be done. What is the implication for the question here? I'm assuming here two ISPs, and assume they have only those 4 BGP routers. Inside they may have many other routers, but they peer at 2 points. That's very frequent. For example, tier 1 ISPs that have global worldwide presence peer at many points here. And assume I have traffic from customer 1 going to customer 2. Which way will it go? Will it go this way or that way? The second way is called hot potato routing. Do we go this way or do we do cold potato routing? So will ISP1 keep the traffic inside its domain as much as possible, or will it get rid of it as soon as possible, or any combination of the two? What's your guess? And the majority think we will do hot potato routing, so we will use this path here, which is the correct answer if we do, for example, like we did in the first example. In the first example, all those 4 routers have the information about all the routes, and if we apply the rule, and if the configuration is the same as in the first example, we have seen that this router will prefer the route that it has learned from eBGP. So it will use this one. So traffic will go this way. So that's the default behavior of BGP, is to prefer hot potato routing, which has an implication that if you reverse the direction of traffic from customer 1 to customer 2 will do the same hot potato routing, will go this path. Therefore, it's very likely that most of traffic routing in the internet is asymmetric. So you cannot make the assumption that if you see a packet in one direction of a TCP connection, you will see the acknowledgements, for example, in the same router. So if your intrusion detection mechanism or your packet filtering mechanism makes the assumption that you will see the two sides of a flow in the same point, this will not be correct here. So routing in the internet is very often asymmetric, and one of the root causes is BGP, the rules of BGP. How are routes put into BGP by the domains to which they belong. This is called originating a route. Well, you can always do static configuration. So you can write a script that will say to each of your routers which routes have to be originated by which router. This is probably what was done in the second example that I showed, where only some routers were showing some of the routes. You can also do something called redistributed connected. That means you can automate this process by saying every router puts into BGP all the prefixes that it is connected to. That's something that is sometimes done. Of course, this works only if all routers run BGP, because otherwise you might have network prefixes that are not attached to a network router that will not be made available. But the classical method, I mean the more sophisticated and more useful one, is called redistribution. Redistribution is a word that means when you put the information that is acquired by one method, for example, a routing protocol, you put it into another routing protocol. So here we redistribute it from IGP, is the word used by BGP to mean OSPF or RIP or IGRP, so the routing protocol inside the domain. If I am a BGP router and I also belong to a domain, so if my domain runs OSPF, I also run OSPF. By OSPF, I know of all the prefixes that are internal routes. OSPF even has a flag to say whether a route is internal or external. So I know of all those routes. Then, an automated and simple way to put that into BGP is to ask this router to look at all the internal routes of OSPF, whether they are directly attached or they come from far away, perhaps even from another OSPF area. Then I can automatically say, put that into BGP. If we do that, it's called redistribution of OSPF into BGP. And the purpose is to avoid doing this through a script here, so that if ever I add one prefix somewhere, I need to configure that on the OSPF router, and the rest will follow automatically. It's good or bad. You might want to automate this if you don't have any security problem. If you want to double check and triple check everything, you may want to have an application that will play the role of the script here and decide by screening very carefully what must be advertised and what not. Those are the three methods that exist. And we will see how they play a role a bit later. Now, one of the very important things that happen in BGP, and also to understand how the things can happen in the internet, is aggregation. Aggregation is possible but limited with IPv4, but is very possible and very desirable with IPv6. Aggregation is when we put several network prefixes and we put them as one single network prefix. We have seen that for IPv4 is difficult to do for the switch operator that serves EPFL and ETH, because the prefixes of EPFL and ETH, for example, are not contiguous, so you cannot aggregate them for IPv4. But for IPv6, they are. For IPv6, the prefix of EPFL is a sub-prefix, is a super-prefix of the prefix of switch. So we append switch delegates to EPFL a fraction of its own numbering space, and therefore switch advertises with IPv6 to the rest of the world, not the prefix of EPFL, the prefixes of ETH, etc., but a single prefix. We have already discussed that, and that's one of the main advantages of IPv6 versus IPv4. Now, the number of routes that exist in the domain, as I said, is 500,000 or more than 500,000 today with IPv4. So there is a huge amount of work that BGP routers have to do. It has lots of drawbacks. First, the BGP tables are huge, but also the IP forwarding table. Whenever a packet comes into a tier 1 router, a router that belongs to Orange, for example, and is at the backbone of the internet, not an edge router, at the backbone, the job of a router is to decide what to do with the IP packet based on which main field If you're a router and you have a packet and you have to quickly put it to one of your interfaces, what field do you look at primarily? Well, in principle, the IP destination address. That's the main job. You may do more sophisticated things. If you're a NAT, if you're a router that is doing intrusion detection, you might be more sophisticated things. But if you're a backbone router, it's very likely that the only thing you do is look up the destination address, and then you have to go through a table of 500,000 entries and find the longest prefix match. So the job is difficult. This is done today by dedicated hardware that optimizes the search and the longest prefix match through those huge tables. And the hope is that in the future with IPv6, the size will decrease. So we want, to make a long story short, we want that backbone routers are able to aggregate as much as possible to make everything simpler. Aggregation is possible. That's the beauty of the longest prefix match principle. But let's see the implications here. For example, here is a scenario with 4 ASs. There's one prefix, this one, 2001 Baba BB, and 2001 Baba BIPF. Those two, they differ by only the last digit. And in fact, the E and F are 2 contiguous digits. F is 15, E is 14. So the only difference is 1 bit. The last bit is different here. So we should be able to aggregate. So this guy will pass the information to AS3. Now AS3 has those 2 paths here. What will it do? Should it aggregate or not? So there are 2 questions here, is whether we can aggregate, and if we aggregate, what is the aggregated prefix? And perhaps a correct answer is A. If we aggregate, certainly it is this prefix. Here I'm showing those 2 prefixes, and I'm showing the binary representation of the last hexadecimal digit. E is this string of 0s and 1s. F is this strings of 0s and 1. We see that we can aggregate them by keeping 1110/47 or 11F/47. That gives the same thing. So this symbolic representation means the aggregation of those 2 here. So it is possible to aggregate them. They are contiguous. Now there's still a problem. The AS paths are not the same. So because this was over AS1, AS3, this was over AS2, AS3. So if we aggregate, can we aggregate when the paths are not the same? Well, BGP makes a provision for that by allowing the OR construction in the AS path, which is given by the curly brackets here. So this AS path 3, curly brackets 1, 2, means 3, 1, or 2. So it means that, I don't know, in fact, what path it will take. It will take one of the 2, and it's AS3 that will know which one it will take. So when I am AS4, I receive this aggregate information. I will not know, but I will know there is AS1 or 2 in the path here. That's one possibility that exists in BGP. If you aggregate and the paths are not the same, well, you say simply the OR using this construction. So if AS4 doesn't like AS1, for example, it will reject this path. If it doesn't like AS2, it will also reject it. So we have lost some information. So in a case like this, it's not obvious whether AS3 will aggregate or not because there's a loss of information. However, if there is no aggregation done by AS3, AS4 will have the same question. And for example, if AS4 decides to aggregate, it will give this path here. So let's assume that the aggregation is done. And in addition, let's assume there is a backup link that goes directly from AS2 to AS4, a backup or a non-backup link. So there is this connection. Therefore, AS4 will now receive the aggregate route with this AS path information, and the specific route, which is a subset of this one, with AS path 2 only here. Which of those 2 routes will the decision process choose in AS4, in BGP routers in AS4? And the majority says B, but this time majority is wrong. I said that a BGP router selects only one route for any given destination. But here there are two destinations. Overlapping destinations are not considered to be the same. In fact, if you would do that, you could have a chain of overlapping destinations, so you would have problems to decide what is a single route. So in BGP, different network prefixes, even if they overlap, are considered different. So the rule of BGP is you pick exactly, or zero in principle, exactly one route to every destination prefix. But if there are overlapping prefixes, you may pick one route to each of the overlapping prefixes. So here it's quite possible, and very likely, in fact, that AS4 will keep both. So AS4 will have a route to this and a route to that. It will keep both. So if you had looked up the next question, you had the answer to the previous. So assume the decision process in AS4 designates both routes as best, so it keeps both of them, right? Now assume there is a packet in AS4 that wants to go to this network here, the bottom blue here. Which way will it go? Everybody says B, which is the correct thing. Here I'm anticipating by which mechanisms BGP will pass the information into the forwarding table of the routers, but hopefully this will happen through some mechanisms. So all routers in AS4 will know a route for this prefix that go this way, and for that prefix that go that way. Now if I have a packet that goes towards this, in the routing table, I have two entries that match this. I have the compressed entries, this one, that aggregates both, and the less compressed, the blue one. The principle of IP is you do the longest prefix match, so the more specific route. So you will choose the more specific one, the more specific route, so it will go this way. Now you could say, why do you need both? Well, this is precisely to provide some more reliability to the internet. BGP keeps only one route, but we have lots of overlapping routes, which gives a lot of alternative paths. And this is one example. Assuming this link fails, then what will happen? AS4 will detect that the BGP router in AS2 is no longer able to speak with me. So the keep alive mechanism will detect that the adjacency is lost. So the BGP router that has the edge here will look up the other possibilities it had, and all routers in this will collaborate to find what is the best. Now, if there is no other best, then this is simply deleted. This is removed from the routing table, and in the routing table, there will be only this entry. Now, whenever a packet comes with destination this blue network at the bottom, it will have only one entry to match, and it will go via AS3. So with this mechanism, with this form of aggregation, we have achieved in the internet, well, the possibility to have more specific routes that may well correspond to more specific paths to go to these routes. For example, that's a very frequent case that you mentioned the case of Google. Perhaps AS2 is Google. So AS2 wants to connect to a lot of, a Google data center here, for example, may want to connect directly to a number of other parts of the world, but still be connected by a default mechanism that goes via a non-optimal path, but that non-optimal path may be used if there is a failure in any of the other paths. That's one of the things that is a constant obsession when you're designing BGP strategies, what rules to put in your BGP routers. You want to provide connectivity in spite of all possible failures that may occur. This is also what makes the internet very successful. It's very rare that you lose connectivity from one place of the world to another one. We will see that some cases occurred in the past, but they were more the results of attacks than the result of failures. Now we dive deeper into the BGP routers, into something that we might ignore at the first approximation, but still will be useful to give us more than a mental model of how BGP works. I'm applying here the rake philosophy. Here we go in detail into one of the aspects of BGP. How does it interplay with the routing protocol inside the domain? What we have, in all the examples I've shown before, I have things like this. So I have clouds. I did as if an autonomous system was a router. But in reality, as we have seen in the fundamental examples a bit before, there are BGP routers inside an autonomous system. There are also non-BGP routers. How do they play together? So the main thing to do is BGP learns a lot of routes, and the job of all this is to put into the routing tables of all the routers of the world how to go to every possible destination. By which mechanism is it done? Right. So there are essentially two mechanisms that very often occur in parallel. The natural mechanism, the one you read in textbooks, and the one we will do also in the lab, is to redistribute BGP into Ospf, for example, into the IGP. We have seen what redistribution means, and we have seen it in the direction from Ospf into BGP. We said one way to advertise all the routes that exist in the internal routes of a domain is to redistribute internal Ospf routes into BGP. Now, the converse is a way to make the routing possible, the forwarding possible inside the domain. All the BGP routers learn about other routes that are outside the domain, external routes. Well, they can redistribute them into Ospf. How is it done? It is they redistribute the routes that are learned by BGP are passed to Ospf as if they were directly connected. So when a BGP router knows of an external route, then it will say to Ospf, I know how to go to this prefix, and typically it will give also a weight that is large to account for the fact that it's an external route. This works with sophisticated routing protocol like Ospf, might not work with other IGPs like RIP because of the size of the number of routes. BGP routing table might be, a BGP information base might have 500,000 entries or more. Now, in Ospf, you can have topology databases that have 500,000 routes. Ospf was made to manipulate big tables. Other routing protocols that we will see in 2 weeks, like RIP, they cannot do that. They have methods that break if you have 1 million or 500,000 entries. So because of that, there's another method that has often been used, is simply saying this BGP router doesn't put it into, redistribute it to the routing protocol, but redistributes them into its forwarding table. In that case, we say injection more than redistribution, although the two words are sometimes interchanged. In this lecture, I will use injection to say that I just put them into this router. The routes in that case will not propagate. That helps only this router, right? By default, in the software routers that we use in the lab, this is always done. You cannot configure your BGP to not do it. So whenever BGP learns a route, it puts it into the routing table. In fact, those versions of BGP, they don't have a separate RIB, routing information base. They don't have a routing information base that would be separate from the routing table. They put everything in the same bag. So this is done by default here. Let us see an example of redistribution, which is the clean normal thing that you should do normally. Here, R5 speaks to R6, so by BGP, they are external peers, so we call that eBGP, and it makes R6 aware that there is a route 18.1, and the next hop is 2222, this IP address here, which remember is an IP address that is considered by X as being internal, so it is in the Ospf of this domain here. Now, if we do redistribution, R6 will redistribute this route into Ospf. So it will do as if it had a port here on which there is the prefix 18.1, as if it would be a route that would be locally attached to this router. Not exactly. In OSPF, there will be a flag, a field in the tables that will say that this is not an internal route, it's an external route. There are multiple ways to do it in OSPF, but classically, it practically means that the cost of going to this destination is going to be some high value. Then, once this is in OSPF, then if this is a single area OSPF, the topology database in all the routers will know that R6 is connected to something called 18.1. Therefore, all routers here will have this information, in particular R2, and R1 will have this information. They will run Dijkstra, and they will, now in this information, there will be the next hop, so they will know that, in fact, this route is reached via this next hop, so they will run Dijkstra to this next hop in order to know how to go to 18.1 here. So if there is a packet to this destination, 18.1, that arrives here at R2, for example, through OSPF, it has found a path that goes to this one, so it will eventually work and find its way to the outside. So that is the more natural approach to pass the information if we have OSPF and BGP here, right? As I mentioned, very often, not very often, but in the past it was very often avoided, less today because OSPF is becoming popular and can support redistribution. But if you have a system that does not support redistribution, and for other reasons, some router domains that, even if they run OSPF, they don't want to merge all the two things, so they don't want to put all the problems of BGP into OSPF and the problems of OSPF in BGP, so they don't want to do redistribution. If you don't do that, then you do only injection, and then how do you, you will need to do a number of other things, as we'll see. Right. So assume, for example, we do only injection. So R6 puts into its routing table the route to 18.1.16, and similarly R2 here. What will be the next hop for this route at those two routers, R6 and R2? The majority says C. Well, this is a tricky question where the correct answer should be B, ideally, because if things are done well, in order to go to this destination, the next hop at R6 is 222, okay, that's fine. The next hop at R2 should be this one. To go there, I send to R1. So the correct answer should be B. Right. Now, of course, there is no way for R2 to know that. It will know to R1 because it only knows this thing here. In reality, what will be done is A, which violates the principle of what we saw before for IP. In principle, in the routing table, we put a next hop, that is the next router to go, or the final destination, and the next hop, by nature, must be on link. Otherwise, it's not the next hop, right? That's the principle of IP forwarding. Well, because of avoiding redistribution, all the stuff, things have emerged to be a bit differently. And today, what routers do, they allow to write as next hop something that is not on link. And why is that? That's because of BGP. Exactly in this case, what do I know in this here? I am router R2. I know that for this destination, the next hop, which is the BGP next hop, which is a field written in the BGP routing information base, is 222. So it's very tempting to write into the routing table, well, the next hop in order to go there is 222. Right? If I do that, it works only if we allow what is called recursive table lookup. Recursive means, what does recursion mean? Well, recursion applies to a function. We say that the function is recursive if in its definition, when you execute the code of the function, you have a call to the function itself. So you have a circular definition. You hope that when executing it, the sequence of arguments that you will pass to the functions will be such that you will not have a loop in the execution, that you will end up into a base case where you can solve the things. For example, you can define factorial n by factorial n is equal to factorial n minus 1 times n if n is larger than 1 or larger than 0 and is 1 otherwise. That's a recursive definition. Here we have a recursive table lookup in the sense that if I put into the table 222, like I will do here, assume I am router R1, and I say to this destination, the next hop is, or another example here, assume to this destination, the next hop is 22263, right? Which is not on link. Then I will signal that it is not on link by saying there is no interface definition. Normally in a routing table, you have the next hop and the interface to which you should go, and perhaps also the MAC address that you have resolved using R. Recursive table lookup here means if I have a packet that goes to 10.1. something, I go to the routing table and I find 222.63. And I still don't know what to do, but still there is an improvement compared to the previous step, is that now this next hop is not on link, but is inside my domain, which means OSPF has found a way to route to this one. So I hope that in my routing table, somewhere else, there is another entry for 222.63, which is the true next hop. So the true next hop of 10.1 is not 222.63, but is this one. This is how things are done with BGP routers. What's the benefit of doing that? Why do we do it in this way? Well, what we want is to separate what happens with OSPF and what BGP. BGP creates this next hop, this entry. OSPF creates that one. Each of the two can change. BGP can change its decision, as we have seen. When a BGP router goes down, what was the best route may no longer be the best route, so the next hop may change. Similarly, this entry here, the second entry, may change because of changes in the topology of the domain. A link or a router goes down. So by keeping those as two separate entries, we make sure that we keep flexibility and we can resist to any failure that can occur in the two things, at the expense of having to do two table lookups for every packet that we forward. So this is what would happen with this here. When a packet goes to R2, R2 will go to its routing table. The routing table says the next hop is 222. 222 is not on link, so R2 will go again to its routing table and say, how do I go to 222? Now this is an internal route, so OSPF knows the next hop is R1 East here, so the packet will go to R1 East and will at least have found its way to R1. Voilà, next week we will see how the packet can go past R1.